Alright, so you guys have been learning about exponent rules and practicing recognizing common exponents of numbers. And we're going to now use both of these skills to be able to solve certain equations where we have an x or some other variable in the exponent. So by now you've learned how to solve linear equations where we just have numbers added and multiplied with x. You've learned all about solving quadratic equations where we have x squared, x with a 2 in the exponent. But here we have equations where the x is part of the exponent. And this is going to be the first way that we learn to solve these equations. This method does not work for every equation that you could come up with. It only works for certain choices of numbers. And all of the chosen numbers on this page and on the ones that you'll be expected to do are on that common exponents page. They're basically an easy number raised to some other integer power. So for example, we'll see here in a second, 16 is 2 to the 4th. So I could think about this a couple different ways. I know that 16 is the same thing as 2 to the 4th. This is on the common exponents page on Canvas, or you could just check it yourself. 2 times 2 times 2 times 2 does equal 16. So I'm going to replace 16, I'm going to turn it into 2 to the 4th. So I'm going to write this equation again. 2 to the x equals 2 to the 4th. And so hopefully you can tell that for these two sides of the equation to be equal, the exponents must be equal. So we can circle these. When everything else is the same base on both sides of the equal sign, there's no other things multiplied or added or anything like that, we have these exponents must be equal. That just gives us the answer, x equals 4. So we basically looked for a way to replace this number with something that would make these two sides match, and then we could make the exponents match. All right, let's see another example. Now, 1/9, 9 is 3 times 3, so 3 squared. 1/9 then is 3 to the negative 2. When you write it on the bottom, the exponent becomes negative. So 1/9 is 3 to the negative 2. So I'm going to replace 1/9 in my equation with 3 to the negative 2. And I'm going to get 3 to the x equals 3 to the negative 2. I'm going to match these exponents and just find that x equals negative 2. If these were not the same number on both sides, then I couldn't do this. So technically I could have also written 9 to the negative 1 instead of 3 to the negative 2. That would also be true, but it wouldn't match. So it wouldn't help me solve the equation. Okay, now let's see an example that's maybe one step up. We have 5 to the exponent of x minus 2 equals 125. So 125 is the same thing as 5 to the 3, or 5 times 5 times 5 is 125. So I have 5 to the x minus 2 equals 5 to the 3. Now I'm still going to match these exponents. They still need to be equal to each other. but that's not telling me the value of x quite yet. It's telling me that x minus 2 must equal 3 for these two sides to be equal. So then I need to finish solving for x. I'll just add 2 to both sides, and I'll get x equals 5. Great. So far, we've been able to easily recognize what base we were looking for. The base is this number that has the exponent on it. And we were able to easily recognize, based on the other side of the equation, what base we were looking for to help us replace this number with something else, right? Because I had a 5 over here, I could tell I needed to get 5 over here. So I asked myself, what exponent with 5 gets me 125? And that turns out to be 3. The next step is a little bit more work because the two sides of the equation are going to need to both be replaced. So let's see how this works. The difference between this and this one is that I can just multiply 2's together until I get 16. 2 times 2 is 4, times 2 again I get 8, times 2 again I get 16. Okay, I needed 4 2's to get equal to this side. Down here I have 9, and then 9 times 9 is 81. So 27 is not an integer power of 9, meaning I can't just multiply 9's together until I get to 27. It won't work. Instead, I know that 27 equals 3 to the 3. That's on the list of common exponents, which you can refer to help you. Eventually you should get familiar enough with them that you can usually at least have a guess as to which one it is, and then in a calculator you can double check and make sure that 3 to the 3 does actually come out to be 27. So okay, I'm going to replace 27 with 3 to the 3. But if I'm replacing this and I'm getting 3, I want to get the same base on both sides. So that means that I also need to figure out that 9 is 3 squared, 3 to the 2. So I'm going to change 9 into 3 to the 2. And I'm going to change 27 into 3 to the 3. These are both on the list of common exponents. 9 turned into 3 to the 2. 27 turned into 3 to the 3. Notice that I put parentheses here. Whenever you substitute something in, it's a good idea to put parentheses if there's any other stuff around it in the equation, and this is no different. Just like when we plug in a number for x or y, and it's a negative number, you want to put parentheses around it. Same idea here. When I make that replacement, I'm going to put parentheses. Okay, well, I know there's a rule that tells me that I'm supposed to multiply the two exponents on the inside and the outside of the parentheses. So this is going to be 3 to the 2 times x, or just 2x, equals 3 to the 3. Now I can match my exponents and get 2x equals 3. To solve for x, I'll divide both sides by 2, and I find x equals 3/2. Okay, and if you want, we can check and find that this should actually work. If I do 9 to the exponent 3/2, I do get 27. You don't need a graphing calculator for this. You should be able to do it in a scientific calculator, or you can also type it into Google, pretty much just like it looks here. Okay, so that works. So we have a couple more examples where we're going to need to replace both sides, both numbers. So I have 1/4 I'm gonna turn this into 4. Actually, I could do 4, but remember what it says on the common exponents page. We could do 4, but it's usually a better idea to use 2. So 1/4 is 1 over 2 times 2. So that's 2 to the negative 2. And 32 is 2 to the 5. So I'm going to replace 1/4 with 2 to the negative 2. Keep that x plus 1. Equals 32 turns into 2 to the 5. So I wrote the same equation again, but the 1/4 I turned into 2 to the negative 2. 32 I turned into 2 to the 5th. Now I'm going to use the rule that whatever's on the inside and whatever's on the outside of parentheses gets multiplied together. So this would be 2 to the negative 2x minus 2. It does multiply with both of these pieces. Equals 2 to the 5th. All right, so now we're ready to match the exponents. Negative 2x minus 2 equals 5. Let's add 2. Negative 2x equals 7. And then I can divide both sides by negative 2. And I'll get x equals negative 7 over 2 as my final answer. So all we did was replace both of these numbers with one of our common exponents, and then use the exponent rules to multiply, and then we match the exponents together to solve. Okay, let's see another one. I've got 36 to the 3x equals 1 over 216. 36 is 6 squared. 1 over 216 is 6 to the negative 3. I think I can always double check that if I'm not sure. So I don't have to totally memorize them, but it's helpful to kind of have an idea and be a little bit familiar with them. 1 over 216. Do I get the same thing if I write 6 to the negative 3? Yes, so it is the same thing. And I'm very confident that 36 is 6 squared, but you could always double check these things in a calculator and make sure that they are actually the same. Now I'm going to turn 36 into 6 squared. Six to the negative 3. There we go. I probably didn't really need these parentheses, but they don't hurt. Now I'm going to multiply these two layers like we got used to. So I have 6 to the 6x equals 6 to the negative 3. Now I can match the exponents and find that 6x must be equal to negative 3. Divide both sides by 6. X equals negative 1/2. There we go. All right. So we went from needing to replace one side to needing to replace bases on both sides. Now we'll just go one step further and we'll do a problem where we have x's on both sides of the equation. And you'll see that this doesn't actually change the outcome too much because it's still going to be the same process. So 625, 1 over 25. I want to think about what number should probably be the base. And I'm pretty familiar with the numbers at this point, but as you get more used to it, you'll be able to guess a little bit better. And you can see that if I type in 5 to the 3, okay, that's 125. That's not quite big enough. Is it 5 to the 4? Yes. So 625 is going to be 5 to the 4. 1 over 25 is going to be 5 to the negative 2. So I have 5 to the 4 to the x plus 3 equals 5 to the negative 2 to the 2x. You might notice that this 2x is here on the bottom instead of being on the outside, but it actually works out the same. It's fine. Okay. So now I need to use the rule on both of these sides that the exponent inside multiplies with the exponent outside. So I have 5 to the power of 4x plus 12 equals 5 to the negative 4x. So all I did was multiply the inside and outside exponents. And now that I have everything else matched, same thing on both sides, I can make these two exponents equal to each other. So I get 4x plus 12 equals negative 4x. You might be tempted to cancel these out, but that's not quite how it's going to work. If I subtract this 4x, I'll get 12 equals negative 8x. Divide both sides by negative 8. And I will get negative 3/2 or negative 1.5 is fine, equals x. There we go. Okay. So I will have you guys try some more simple examples with these. And let me know if you have any questions. Talk to you again soon.